Friends and visitors from this lab, Wayne, Kreider, and Adam Maxwell, and Jessica, if she's coming. And we'll have two seminars this week. First one is today, and the second one will be on Friday. And both Adam and Wayne will be presenting their lectures. And then they're not maybe too difficult to understand, because most of them will be about the medical applications of ultrasound with illustrations. And today Wayne will speak about lithotripsy, which is a way to break kidney stones, but he'll speak about the special kind of lithotripsy which was proposed recently. And Wayne, you have
half an hour.
Half an hour maybe? Maybe it's up to you, but we'll start.
Thank you, and thanks everyone for hosting us here. It's great to finally visit. We've worked with Oleg Vera for a number of years, and it's a pleasure to be here, finally getting a chance to visit Moscow. So this is actually a project that involves many people and a lot of things, and I'll sort of just give an overview of the many different aspects of it that we're working on. Just to start at the beginning, the basic background is kidney stone disease. So people form stones in their kidneys. It's about 10% of the population, so it's not an insignificant number of people who get this problem. And so for over about 30 years, people have been treated using acoustics. So rather than doing open surgery, people were able to remotely treat through the skin, focus shock waves to break kidney stones, and then the stone would be able to be passed from the kidney through the ureters down to the bladder and eventually out. And so the big advance was that it wasn't open surgery, so that there was much less likelihood of getting an infection and other sort of serious complications. So shockwave lithotripsy, or SWL, is non-invasive, and even though it used to be that the only alternative was open surgery, now there are other techniques, which are ureteroscopy, or URS, which is where you go sort of up the plumbing backwards, and you're able to break the stone and or remove the stones that way. It's favored by urologists because you're able to be sure that you can remove fragments that way. There are some complications, however. And the other one is percutaneous nephrolithotomy, which is where you actually go through the skin using a needle, basically a very large bore needle, and you can then puncture the kidney and remove the stone that way. So those are, at least to physicists, that seems like more invasive ways. I think I've heard other arguments from urologists of what's invasive or not invasive. Ooh. Let's not do that. So that is the basic background. And so in the recent years, certainly in the US and particularly in academic, I think it's mostly around the world, and particularly in academic environments, urologists are tending to favor lithotripsy shockwave lithotripsy less and less, because these other techniques have higher stone-free rates. And so there is now more that, even though shockwave lithotripsy is used maybe on the order of half of all treatments, the amount of its use has been declining. And so there is some motivation for improving the performance of a non-invasive treatment. And so we are looking at ways to do that with all of the things that have been learned over the, say, 30-some years of research into the physics of how do you break stones and how do you cause injury using these acoustic techniques. How can we do it differently? So the approach that we're using is, we call it burst wave lithotripsy. And so the reason is that instead of using a shock wave, which is sort of depicted here, we use now a short tone burst. And the frequency that we pick is relatively low frequency for medical ultrasound. This is, I think, probably showing about 170 kilohertz. The overall peak pressure is quite a bit lower. Things to note: the energy in the burst wave pulse is about the same here, is about the same amount of energy acoustically as we have in a shock wave. However, we're delivering the energy considerably faster rate. So this is the PRF, means the pulse repetition frequency, so the rate at which we would deliver these pulses to the stone. So one of the things is it's obviously a higher energy delivery rate. That means there's the potential for breaking the stones maybe faster or maybe in some more preferred way into small fragments that would pass. So that would get at the idea of having a higher stone free rate. So that's the idea that we're pursuing, and there's the idea is that can you use that extra energy to benefit to break the stones. So just for a comparison, so here's what a shockwave lithotripter looks like, a clinical one. You can see it's a very large device. Here, this part of the lithotripter is actually for x-rays to do positioning. Here is the lithotripter head, so the patient would lie on this table. This sort of dry head would be coupled to their back to have access to the kidney. And then here is the the x-ray imaging. And this is the lithotripter itself, which has a big capacitor, so to create the shock waves, they dump the electrical energy and cause shock waves. I think this one's probably electromagnetic. And there's also a water system you have to couple. There's water in this head and you have to couple it. But you can see it's a very large system. And so there's actually, for hospitals, it's important to know how much space do they have, and there's many different things that influence why they do or don't like to use it. So a typical treatment would look like this. So you see here is a cup of water that's held at the focus of the lithotripter. You see the stone and you see there the stone broke. So you see that there's a repeated, it's about 1 hertz, or maybe that's a little faster than 1 hertz, PRF. The stone is breaking. You see the stone sort of breaks eventually into many fragments, but that there's in some sense, some randomness. The stone jumps around. The size of the stones that break is sort of random, and that leads to a poorer stone free rate because some of the fragments may be big and may not clear. Also, the stone jumps around, it may be difficult to target it. So the idea of burst wave lithotripsy, and this is work that Adam mostly and Brian Kunitz have done at the Applied Physics Lab to develop hardware for delivering burst wave lithotripsy. So this is a transducer. It's quite small. You can see here's a pen for scale. There's a transducer. This is the amplifier. This is a matching network here, and this is the amplifier. It's all quite small. If you mount an imaging probe, an ultrasound imaging probe, you can image through the central hole, and then this is the imager. So this entire system is quite small and handheld. So that in comparison to the very large shockwave lithotripter. Here's a few movies of showing stones breaking. So this is, I think, that one is probably in real time. It's a relatively soft stone and it breaks almost immediately. And here's also a slightly harder stone, although this one seems to break quite easily as well. Not all stones break quite this rapidly. Some of them take longer. They're harder stones. And here's one that actually is done. So the urologists are able to, in an animal, to insert a ureteroscope up through, up into the bladder, and then this was just imaging, so not quite all the way to the kidney, but showing what's possible to do, and we do in our labs in Seattle to do animal experiments. And so you see there are some stones that were implanted into the bladder, and here we're exposing them and show that we can break them. We're not going through the skin here, so it's a relatively simple experiment, but just to show what that looks like. So one of the big advantages of burst wave lithotripsy clinically is that you want to create stones of a uniform size that are clinically insignificant, meaning that they will pass. So it will sort of end the need for treatment for a given patient. And so this is data from a paper that Adam wrote. And you can see that as a function of the ultrasound frequency, the fragment size is able to be controlled. So at the lower frequency, we have some larger fragments. As the frequency goes up to 800 kilohertz, this is almost like grains of sand. So these are very small and should easily pass in the urine. You can also see here on the surface of the stone, these are synthetic stones that we can make in the lab. That's why they're shaped nice and smooth as a cylinder. You can see that you create these fracture lines on the surface of the stone. And our thinking is that these correspond to sort of resonant waves that build up inside, standing waves that build up inside, and shear waves that build up inside the stone. And so a leg has actually used a linear elastic model, and this is just an example of a type of simulation of the stresses that you might generate inside the stone from this sort of a pulse. And I think as we get toward the end of the movie, it will show sort of, these are showing the maximum principal stress at any given point in time, at any given point in the stone. And at the end it'll show the maximum over all time of that stress, the max stress. And you'll see that there's a characteristic pattern to that. You can sort of see it now where you see the reverberations inside the stone.
It's up to 100 microseconds.
Yeah, it's almost done now. I will just go to the end. So there's the max stress. And so you can see that there's some sort of characteristic spatial dimensions. And what you found if you run more of these simulations, those characteristic dimensions of the stress pattern change as a function of frequency. And one of the things that sort of motivated the idea of how to break stones is the work that Oleg, Robin Cleveland, and Adam was involved in this as well some years back, to understand how shock waves broke stones. And one of the key things that was learned from those studies is that it helps to have a beam width, an acoustic beam width that's wider than the stone, which helps to couple energy into the stone and the generation of shear waves, which then is able to break the stone. And so the same idea applies here. You create the same shear waves, you cause the same sort of different types of stress patterns. In this case, because the shock waves, there's only a single wave. In this case, you have many cycles which can reverberate inside the stone and cause potentially an amplification of the stresses inside the stone to break them. So that's the idea. So here were some studies that Adam did. So looking at in water, if you change the pressure amplitude of the burst waves, and I believe this was done at 170 kilohertz. So looking at what pressure amplitude are you able to fracture the stones. And you see that there seems to be a pretty sharp threshold that above about 3 megapascals, stones break. Below that, they don't break. So this is sort of interesting, and it changes the understanding a little bit. It's not just the linear elastic waves inside the stone. If it were, we might not expect quite that strong of a threshold behavior, and there's some other experiments that I won't really get into that also sort of support that. And so one of the ideas is that there's likely that sharp threshold is due to probably a cavitation mechanism. That the idea is that cracks to propagate inside the stone require the stresses inside the stone, but it may be that the surface cavitation helps to cause cracks, or the initiation of cracks, which now gives a place to propagate the cracks and cause fractures. So, and this is also our understanding of how shockwave lithotripsy works. So how should this work in a clinical environment then? So one thing that's also different projects and work in our group is that natural stones have twinkling, and it's an artifact of imaging with ultrasound. And so work has suggested that this is related to bubbles on the stone. And so it may be that all natural stones have bubbles on them. And so maybe that's good. That helps us to break the stones. We need cavitation to help us break the stones. It seems that naturally the surface of the stones tend to trap bubbles, so all is good. However, the story is maybe more complicated because cavitation, while it may play a role in breaking stones, it can also be problematic. So if you have bubbles that are generated away from the stone, they may acoustically shield the stone so that now the waves that you're delivering to the tissue to the stone don't ever reach the stone, so the stone doesn't get broken. Instead, you excite bubbles. Exciting the bubbles can also cause injury. And so there's been quite a number of studies over the years, and this is sort of the PPG group, which is from a group in Indiana, who were experts in renal physiology, a group in Seattle, and other groups who were involved more in the physics and other aspects. And shockwave lithotripsy definitely causes injury to the kidney. So moving on, sort of the next sort of part of the talk, I wanted to think a little bit more about cavitation and how injury occurs. So if we're assuming that there's the ability to break stones, which is its own challenge, but even if you're able to break stones, there's a question is, can you break stones in a regime where you don't cause injury. So as I said at the beginning, we're actually delivering rate. Even though you can cause injury with shock waves, we're delivering energy at 40 or 100 times the rate of shock wave lithotripsy. So there's the potential, in some sense, if we're delivering that much energy, to cause quite a lot of injury. So we have to avoid that. So one of the things our general approach to doing this is we want to have a metric of cavitation. If cavitation is what causes injury, can we detect the cavitation in real time and then avoid it? So we could change the treatment. If we're causing cavitation, we could reduce the amplitude, or pause, or try different targeting, or just stop treating a patient altogether to make sure that it's safe. So how to detect cavitation? Well, ultrasound imaging is actually quite sensitive to bubbles. So perhaps that's a good approach. So however, to do that, there's the need to correlate imaging and detection of bubbles with injury. There's sort of, in the big picture, we have many parameters for optimizing burst wave lithotripsy. This is a very new idea. We've only been sort of thinking about this for maybe two years or so. So what pressure amplitude should you choose? What frequency? What pulse repetition frequency? What duty factor? How many cycles per pulse? All of these things are important. And then, so at the end of this, if we choose a set of parameters, we have a treatment. The idea is that we have a prototype BWL system, which is the same one that I showed a picture of earlier, that has imaging. We can detect cavitation in real time, and now we have feedback to keep where we can treat at as high of a level as we want in order to break the stone, while being sure that we don't cause injury. So the first step in that sort of approach is we need to correlate. We need to be sure that when we think we're detecting cavitation, that really is what correlates with injury. So how to do that? So we did a series of experiments. The data I'm going to show here are from 4 different pigs, so 8 kidneys, and we deliver a burst wave lithotripsy treatment to that site. You see we have a couple of different frequencies here. We use 2 different transducers. This is the same duty cycle, since the frequency is a factor of 2. This is the same sort of overall treatment duration during each pulse. We're using 40 Hertz PRF in this case, which we could use a faster PRF, although that tends to cause more cavitation, and so we pick a number that we think is reasonable. And in real time, we monitor those treatments with B-mode imaging. So that's the standard imaging where you send an acoustic pulse, you receive it on many elements, and you create an image from it. And then there's another form of that, which is Doppler-based imaging, which our group calls twinkling or S-mode imaging. So we look at the consistency of the received waveform. In some sense, we send an ensemble of pulses, and we look at the consistency of that pulses with the idea that cavitation has a randomness to it. And so if the returned waveforms are not consistent, there's in some sense a power that's associated with the bubble activity. So to evaluate our data, we do the exposure. At the end of it, we will then perfusion fix the kidneys, and then we can examine them either by MRI. So we go to an MRI machine, we take a 3-dimensional image of the space, and we try to detect hemorrhagic injury, so anywhere where there's bleeding. We also do it by sending it to our colleagues in Indiana, and they will slice through the kidneys and look on each section for, is there blood present in each spot? And so we can detect, was there injury, and then we can correlate that with, did we detect cavitation in our imaging, or what we thought was cavitation. So this is just I have already more or less said this. This is the cartoon that our group has been using for the pig experiment. So we actually do these treatments. We're not going through the skin yet. We can control the pressures much more carefully if we apply directly to the kidney after opening the abdomen of the pig. So here's what the images look like, and I hope these will show up well. If you look, there's very faintly on there's a red ellipse I'm outlining there. That's the focal region of the transducer, and so if you look at that while I play the movie, this is what, on just B-mode ultrasound, what it looks like as cavitation develops, or what we think is cavitation. So there you see right here it's beginning, and then it continues, it's grown and it's moved towards the transducer. The transducer is at the top, and so you can see it's quite large there. So if you spend a good bit of time looking at these and the image is better than what it looks like projected, it's fairly straightforward to detect, but if you were to try to train to automate that by the image, you can see that the contrast in terms of overall amplitude is not that high. What we're actually doing is you're looking, I think, our own visual processing. We see how it changes from frame to frame. And that's really what the Doppler imaging is doing, is it looks at the consistency of that ensemble of pulses. And we do that, I think, fairly naturally when we look at this frames by eye. We can see that there was a change from frame to frame. So I won't bother. This is another one. Well, I guess I will. It's just another example of how this looks. And I think this one is maybe even easier to see. There it is. It's very drastic right in the middle. And these you can see, obviously they weren't synchronized. So the interference, these lines like this, are because we did not synchronize the imaging with the therapy. We can do all of that. These were some of the very early studies, so there's many things that we can do. So this is, I mentioned the injury, this is an example of what the hemorrhagic injury looks like. So after the kidney's been fixed, you see there's a surface, there's a hematoma here on the surface of the kidney where we've caused bleeding. If you were to section through it, here is you can see the region looks like it starts in the middle of the kidney around the collecting space. And then proximal to that, near the transducer, there's hemorrhage throughout that space. I don't think there's too much more to see from that slide. So here's looking a little bit more, thinking about the imaging and how we detect injury. And I apologize, there's not really too much to see here, but if you were to look at just the B-mode echogenicity, so if we were to draw, and again, it's drawn on my screen, it's just very hard to see here. There's a rectangle here as a region of interest. And if you were to look at either the average or the maximum value of the echogenicity, the intensity of the image at each pixel, the average value, you can see it's very consistent until you get to about frame somewhere near 200, then there's some increase. It's obviously much less clear in the maximum. There's quite a bit of noise there. It's hard to know what that means. If you go to the Doppler signal, yeah, this before and after cavitation, that label isn't quite right, is it? Because I guess it is correct, it's just hard to see on here. So you see here, I have actually artificially colored in green if we exceed a threshold, but you can see that it's somewhere just before frame 200. This is when the transition happens here. You can see that we have a very good indication of this on the Doppler imaging. There's a very sharp bar. I think it would be very easy to detect that automatically. So just as these are the things that we did. Here's what the morphological examination of the kidney sections look like. So here's the fixed kidney. Here's the region you can see there's hemorrhage. It's fairly easy to see these if you spend time learning the anatomy and looking through the images. On MR, there's its own sort of lots of details that I won't get into. We look at both T1 weighted imaging, T2 weighted imaging, and there's a susceptibility weighted imaging, which is designed to detect the hemorrhage. And it's sort of easiest to see in some sense with the anatomical structure on the T2. And so here you see there's a region that corresponds to injury, which is more or less analogous to this site here. So to summarize, at the beginning of all of that, I said that we had 8 kidneys. So we actually treated the upper. We applied a BWL treatment to the upper, the middle, and the lower pole of each kidney. So that's 8 times 3, so 24 different sites at which we could do comparisons. We have MR of all 8 kidneys, and we have only the ones with the dashed lines. We have the morphological examination from the sectioning, so these 5. And then we compare in a place where we had a dose. So the bracketed number here indicates the seconds of duration over which we observed cavitation by the ultrasound imaging. So, for example, at this site, there was we applied a treatment, but there was no visible cavitation. Here we didn't even apply a treatment. In the middle, we applied a treatment, and for a little over 2 minutes, we observed cavitation. So if you go through all these sites, and the yellow means that the imaging in some sense was sort of ambiguous, how to interpret it. So if you go through all of the sites and you say, if there was a cavitation dose from ultrasound imaging, was there an injury, and you correlate those sites, at 14 of the 15, or not injury, so you're correlating both the presence and the absence of injury. So at 14 of the 15 sites, remember there were only 5 kidneys that we looked with morphological examination, so 15 sites. 14 of the 15 sites were consistent, where cavitation detection by ultrasound matches the injury detected on morphology. 20 of 24 sites if we do it by MR, and if you compare the injury detection between MR and morphology, it was about 13 of 15. And if you go through and look carefully, the ones that don't agree in particular here, this one, it's this site here, and we think that this is because there was such a huge injury at this spot, and this particular pig, we were trying to cause injury, so we kept exposing it for quite a long time, even though we knew that we were causing injury. It looks like some of the bleeding at the upper part of the kidney actually bled in through the collecting space and maybe into the sinus region of the kidney into this lower pole area. So by our detection metric, it says that maybe there was some injury at that site, although it's ambiguous. So it's not clear that we actually didn't have a good correlation. So it seems that our strategy is going to be feasible, that we can detect injury before we cause it. So we detect it on ultrasound. We could, in theory, stop before we've accumulated any detectable injury. And the injuries that we're detecting, just to give a sense of scale, we can detect extremely small injuries. We're detecting down to injuries less than 0.1% of the functional renal volume. So that's what the urologists care about, because you're not losing function of your kidney. If it's less than 0.1%, then it sort of is, by sort of the conventional standards of how they've been doing this is sort of insignificant. So here is, the next question is, okay, if cavitation is what is causing injury, we have to avoid it. There's the question of where can we, in what pressure ranges can we break kidney stones? The question is, can we break kidney stones at pressures that don't cause cavitation? So one of the things that we're very interested in is, what is the cavitation threshold in a kidney? So this is sort of a compilation of many of the same pigs as well as a few others, to try to say what is the cavitation threshold in the kidney. So the first ones, with our first transducer was at 170 kilohertz, and so this is sort of challenging to interpret in some ways. So this is again at site number. So we have 3 sites at most in each kidney, and so if it's this sort of reddish purple color, that means that we did not observe cavitation, and so if we're searching for a threshold, we could potentially search at a lower pressure. However, for whatever reason, and there are various reasons during the experiments, we didn't search at a lower pressure. So we would say that the threshold is something lower than a red circle, the exact opposite for a blue circle. That's the highest we tested, and there was no cavitation, so potentially, so the threshold should be higher than blue. And if we had both a red and a blue at the same site, we say that I draw an X there instead and say that I assume that the cavitation threshold is halfway in between. So if you look at 170 kilohertz in these initial exposures, we're lower than this, we're higher than this. You can see we're very clearly sort of zeroing in on a pretty clear threshold, somewhere here around 5 megapascals. And then these next few, which are sort of strange, which sort of messed up our correlation a little bit. Not sure what to make of that. And then we did the next round of exposures at 335 kilohertz. And the reason that we're interested in this frequency is because, as I mentioned earlier, higher frequency causes smaller fragments. And smaller fragments, this is the appropriate size of a fragment that urologists would be comfortable with, or it's close to it, that they would easily pass. So if you're trying to make a patient stone-free in a single treatment, you want to make all of your fragments approximately this size, and this is what we think we can control well with burst wave lithotripsy. So here, it should be higher than the blue circles. So for all of these sites, we turned up, and this was as high as we can turn this current transducer. We never achieved cavitation. So we say, great, the cavitation threshold should be above 8. However, we have one here where it says it should be below 6.5. We have others where we got both and it looked like it's around a little above 6. And so in some sense the story is not so simple. We have less clear data on what exactly is the cavitation threshold for this type of, as we're detecting it with ultrasound imaging, what is the threshold? I think we have some ideas for doing these experiments in maybe a more clear way. I suspect that because at these sites we never achieved cavitation, so when we go to the next site we would usually start at 8 megapascal, then we would see cavitation. So, but now, and we would usually, once we did that, we would wait for, say, 2 minutes to hopefully let bubbles dissolve, and then we could retreat the same site. However, there's nothing saying that the bubbles would have to dissolve in 2 minutes. They could be stabilized by various sort of surface chemistries. So they should have dissolved by then if you do a simple calculation, but presumably it may not be so simple. So it may be that these very low values that we're seeing are due to the fact that we saw cavitation at something above what was the true threshold, and then the apparent threshold was actually lower. So sort of the conclusions from all of the injury-based things. So it seems that we are pretty well able to use ultrasound imaging to detect the cavitation threshold, which correlates with injury. This means that we have a pretty good strategy for developing real-time feedback for BWL treatments. And so that's something that is not currently available for shockwave lithotripsy. So from the cavitation threshold data, we can say that it looks like the threshold at 335 kilohertz is higher than 170 kilohertz. As you would expect, a higher frequency should have a higher cavitation threshold, but there's still a bit of a range there. It's a little bit unclear, a big exact number. But the big conclusion is that regardless, the thresholds were around 5 or 8 megapascals, something like that, in that range. And yet we were breaking stones, if you remember an early slide, at 3 megapascals and above. So it seems like there's a range where we can work to try to develop a proper treatment. So ongoing things that I'm interested in are how are we going to understand the BWL-induced cavitation. So one thing would be a simple diffusion model. And so this mimics a paper that sort of Oleg and Vera and others in the PPG group worked on a number of years ago, which was simply if you have a single bubble, you can calculate during the dynamic part of its excitation how much gas, non-condensable gas, diffuses into the bubble, and then you can see in between while it's quiescent, so there's no acoustics applied, the bubble should just be sitting there, it should be slowly dissolving. You can calculate how fast it dissolves and whether bubbles that you excite in one pulse should be around for the next pulse. So that's a simple thing that we can do, and we've already done some of those calculations. That's part of how we came up with the 40 hertz PRF that we're using. Other things, part of our extended PPG group are that we have collaborators at Caltech in Illinois who are modeling bubble clouds to understand the acoustic propagation through bubbly fluids, as well as how those bubbles, when excited by acoustics, are going to cause injury. And as a part of collaborating with them, we're working to develop sort of an in vitro test environment in which we can look at the bubbles using high-speed photography. We can image them at the same time so that we can understand what does an ultrasound image mean in terms of the optics, which we can maybe more easily translate to initial conditions for a model. And this is a movie, I should play it. This is in a polyacrylamide gel showing the evolution of a bubble cloud. So one frame is captured during each BWL pulse. And so you can see that there's some cloud in the gel that sort of initiates and evolves over time. So we can image these gels with ultrasound at the same time and then see what does an image look like. If you see a certain signal in an image, what does it mean in terms of how many bubbles, where are they? So we have sort of tools to investigate this. And so important questions that are sort of out there for us. A big one is we can investigate injury without a stone, and that's easy to do. It's actually very hard to do an animal experiment with a stone. But in theory, you could have an acoustic reflection from the stone, and the cavitation threshold might be lower with a stone. So can we test that or figure that out somehow? Another is if we are using twinkling imaging to identify a stone, can we tell if there's the injurious cavitation separate from that? And then lastly is how long can we let cavitation on without accumulating injury? So we were looking for threshold, but the next question is how much injury is sort of tolerable. And just like to acknowledge, as I said, it's a large project with a lot of people at LIMU in the Applied Physics Lab, in Urology and Radiology, as well as collaborators at other institutions. And that's a view from behind our labs in Seattle, so it's a little dark, but it's nice with the water. Our labs aren't always the most beautiful buildings, but we have a nice view. So.
Thank you. That's very nice. If anybody has questions, please ask. Timothy?
Thank you. Does the result mean that the only reason for injury and hemorrhage is cavitation, but not the propagating signal itself?
That's the current theories. There was actually one of our collaborators, John Friend, proposed that you could have cumulative shear, that as a shock wave would pass, there's a structure inside the kidney called the papilla, that as you would pass the papilla, each shock wave would slightly deform it, and then it wouldn't quite recover before the next shock wave, so you'd accumulate some sort of shear displacements that would ultimately cause injury. It's a proposal. It's hard to test these things, but the one that everybody accepts is cavitation, and the fact that in our experiments so far, the fact that we can detect it using strategies that are designed to detect bubbles, and so far the correlation seems to be good. So I think we're adding to our understanding that it probably is just the cavitation, but it's hard to rule out because as you turn up the power, perhaps many things are happening.
I think it's also discussable in case of shock waves when you have thin shock and then you have shear stresses, but here the waveform is smooth, there's no shocks.
So there shouldn't be any problems, although it's maybe a hard thing to prove a negative.
Right. More questions? Actually, although I quit this talk before, but I still have the question. You said that the conclusion was quite important, that you can break the stone without causing cavitation in tissue. On the other hand, you said that to break the stone, you need cavitation on the surface of the stone. So that means that the cavitation threshold for the stone bubbles is much lower than how low? So do you think that without bubbles you can break the stones?
So I don't know. So these are sort of active areas of research. So I know Adam has been interested in doing experiments in castor oil, so you can reduce the cavitation that way and see is it possible and at what pressure amplitudes could you possibly break a stone in the same way without cavitation. That requires perhaps a very big transducer and amplifier to try that. So I think logically there is sort of a hole in that, as you're pointing out, that you say you need cavitation, but you don't want cavitation, and it's this threshold and the other threshold, and how does that work? And I think the part that's hopeful about it is that shockwave lithotripsy has done exactly the same thing for 30 years. Is they say that they probably need cavitation on the stone to help break the stone, and yet they're able to apply the treatments in a way that causes minimal injury. So
and another thing that, just to clarify, you mentioned 40 kilohertz, 40 kilohertz repetition frequency, right?
just hertz, 40 hertz.
40 hertz. And you said that you chose this PRF based on the modeling, so that what would they dissolve before the next pulse comes. So in experiment, did you try to send like more frequent? Did you see any difference? And another way, I have the question: if the PRF is the parameter which also should be involved in the cavitation characterization?
Yeah, it definitely should. This is the problem of we have a limited number of pigs and treatment sites and many parameters, and so the PRF definitely has an effect. We've seen that. In terms of quantifying it, it's very hard to know. The renal physiologists may make it harder for us. They say that we should only look at the first treatment site in each pig because you might have these physiological feedbacks and restricting blood flow and various things. We're trying to ignore that, hoping that that is not an effect, but ultimately to publish papers on this, we will need to answer their questions and concerns. And so this is why so far we've seen some of the effects, but we're not really studying them yet because it's very hard. We don't have enough sort of treatment sites, and so that's the coming years of the grant. We will continue to design more studies, and we're trying to be judicious with how to do those studies and get the most information out of each animal that we treat.
Wayne, I thought that this question appeared several times before, and I kind of remember the answer that there was a cavitation threshold for stone, which was about -2, -3 megapascal, and about -5, -6 for tissue. And how this threshold was measured, was it twinkling with artificial stones, or so somehow it was measured and it was lower pressure to twinkle the stone rather than to twinkle the tissue.
So I'm not as familiar with the studies on twinkling and raw
Or
tissue.
maybe not twinkling, maybe PCD, or so the threshold was, I remember the number, it was like 2 or 3 megapascal comparing to 5 or 6 for tissue.
So those are measurements of when the stone breaks versus when the tissue
okay.
breaks.
Okay.
So
Yeah.
the tissue, the stones break at 2 to 3 megapascals. The tissue
It is not
is
injured.
damaged at 5 to 6 megapascals. So I
So
think
it's kind of
coming back to
implicit.
Oleg's question is stones are special in the body because they're solid and they can hold large bubbles in the crevices of them, and soft tissue does not seem, there's a lot of evidence that suggests there are very few large bubbles in the tissues in the body, in the soft tissues. So stones in particular have, I think, a unique feature about them that they twinkle because they already have more bubbles on them, not necessarily that, and you know, those bubbles, if they're larger, have a lower threshold or lower pressure threshold for cavitating than small bubbles, which seem to be the only ones in tissue. So it's just that stones are just a good a place to where large bubbles can exist more likely than tissue. And so it's just more likely that you're going to produce cavitation on a stone before you produce cavitation in the tissue.
So and this is one of the, we're still trying to get the right phantom to make it work, but so we think that there's likelihood that you have cavitation around the stone, and if it's just on the surface of the stone, then maybe that doesn't damage tissue. The stone is in fluid space in the collecting system, and you might cause a little bit of injury to the lining of the collecting system, but maybe that's a negligible amount of the functional space or functional tissue of the kidney. But what is the likelihood of, if you have cavitation here, the likelihood of somewhere else nearby where you can injure tissue of initiating another bubble cloud? And so we can look at this if we have a proper phantom that sort of confines the bubbles in the stone into a certain volume, of seeing what's the likelihood of changing. So we can do it with a stone or without a stone, and what's the likelihood of generating a cloud of bubbles that we sustain. There's some technical challenges on making a phantom that properly resists cavitation and sort of does all of the things we want, but we're hopefully getting close to being able to look at some of those experiments and hope to, that would help to make a convincing argument that, okay, that we think that we measure these experiments in the pig, and it looks like the threshold, as Adam said, where you break the tissue or cause injury, is 7 megapascals, say, at 330 kilohertz, and maybe we say that independently that when we do this in vitro, that the presence of a stone changes it, reduces it by, we think that maybe by most a factor of 2, but maybe we say it's not a factor of 2, it's a factor of 1.3.
But I think that also the important point that you monitor the cavitation, so once you have it, you stop.
So this is, I think, the strategy that makes sense to me, that if you want to argue to the FDA or somebody that this is a safe thing, that it's not dependent on saying that the operator can only go up to this pressure, it's saying that you actively monitor it, and so as long as you avoid some dose that you're measuring in real time, then everything is fine. And that way we can also be aggressive with the treatment, that maybe a patient has a really hard stone and you would like to use as much energy as you could, and if you had to set a single threshold for all patients that you know is safe, you may never break the stone, and maybe for many patients you could treat quite a bit more aggressively. And so
to make the discussion maybe simpler, I have another question. So you showed this big, huge system, lithotripsy. It was about the size of this room, maybe half of this room.
Mm-hmm.
And you said that this BWL device will be much smaller. How much smaller?
So here it is. So I think you could fit, it's an imaging cart. So a
But
cart,
then the imaging card is huge again, so it's not portable.
It is portable.
it's on wheels. They wheel it all around campus to go to the
Okay,
clinics.
can you have, is it enough to have like laptop size?
So you see here, so there's a tower computer, which could be, we have another version that's a very small computer, just bigger than a laptop. So the screen is here, so we don't need a laptop. Right now we need the Verisonics, so the hardware of sending and receiving the acoustic pulses. So that is, the size of a very large computer tower, so that is still sort of fixed. We can't go smaller than that with imaging. Although I guess there's other commercial products that maybe are maybe even smaller than a Verisonics, but for our current implementation of it, it requires something like that.
There is a system that comes on a tablet computer that just plugs an ultrasound imager into it.
Wait, maybe Adam, can you tell something about the astronauts and some motivation for the space devices? Because students, they don't know about this part.
So another area of research in our group, we have a lot of work for the National Space Biomedical Research Institute, so NSBRI. The issue is that astronauts, because they're not in gravity, their bones aren't being loaded, and so one of the physiological feedbacks is normally your bones are actively, you're creating bone and you're reabsorbing bone always all the time. And if you remove what the stimulus to create bone is that you have forces on your bones, and so you take yourself out of gravity and you have much less force on your bones. And so you tend to demineralize your bones, which means the mineral goes somewhere, it's in your kidneys. They tend to get kidney stones. It's a big problem on the space station and other places. And so
they always stopped one of the mission. It was Russian mission to the International Space Station. And our cosmonaut, he had a kidney stone. And you can do nothing in this space because there's no doctors. You have your stone and you have this problem.
And what is the typical time of growth in space?
typical time of what?
Growth of the kidney stone in space?
I don't know.
Weeks or
might know better than you,
years?
but
This Russian cosmonaut, he was checked. All of them are checked, so they are quite healthy.
Absolutely clear before the...
Yeah, he was like a couple months in space, I think, and then he had this done.
Probably months.
So this is going back to the beginning. So if you're on Earth and you have access to good doctors, there's other surgical techniques, but obviously the less facilities you have, you need to be sterile environments. You need to have special skills for a surgeon and/or special equipment to do the other techniques. And so this is another advantage of the non-invasive techniques. Is maybe you could do it in space, or maybe you could do it in more remote areas where you lack the infrastructure to be able to get the other treatments.
So in this sense, making the systems more compact, it's not only because we have space here. We can have big rooms for the equipment, but it's not only cheaper, but also it's portable, it's compact. So the applications where it's critical, like in space, for instance. Yeah.
I mean, they're very expensive. A lithotripsy is a very expensive piece of equipment. There are only 10 in Canada, which is 22 million people. So 22 million people, if 10% of them get kidney stones in their life, is affecting over 1 million people. And in each, there's 13 provinces in Canada, and all of them almost go to one hospital to get treated within that province. And so sometimes they have to wait for even weeks or months before they get treatment because there's a huge list of patients getting treated on those machines.
It's like when
So-
reported about New Zealand experience that when they have these German trucks, big trucks with a and this truck goes from village to village.
Mm-hmm. So that every 5 weeks the truck goes to your town and treats all the people with kidney stones, and then moves around to New Zealand and treats all the other towns. So
And they
this
collected with more than 10,000 cases, right?
yes, so
finally they showed
11,000.
data for 11,000 cases treated on the truck traveling from village to village around New Zealand. So they found patients in different places that were waiting for procedure. That's very nice statistical data.
Were they waiting themselves or were they diagnosed?
We're not clear how they manage that because probably the itinerary is known, and if there's a patient that can wait, so they wait when truck is coming.
No, they were diagnosed. So when truck
But they
comes
were
to
not
the village,
diagnosed this exactly day when the truck was coming.
Ah,
They were diagnosed.
so they didn't know that they had this.
They either wait or if they cannot wait, they would wait another way.
They'll do surgery or some other procedure that Wayne talked about. They can't wait. So
Just maybe some small comment that medical equipment usually develops like smoothly with small improvements, and sometimes new technologies come, and they don't come very often. So the shockwave lithotripsy was invented in 70s, so that's already a long time. And after that, just 2 another minimally invasive procedures were invented. So this one is actually among these few ones that were proposed. So you are kind of listening to a very new technology that is coming to this medical world. So it's a very beginning of this, but already it was presented at several urological world congresses, and doctors are very interested because of several advantages of this new thing.
So yeah, another part of the history is that shockwave lithotripsy, the first clinical treatment was in 1980, something like that?
1980, yeah.
And the results that they got back then are maybe better than most of the results that they get now. So there's been very little improvement over the years, and so that's one of the reasons why other new technologies have come along and are maybe, at least for many cases, urologists prefer it. And so the hope would be that it's time for some improvement, and because people have studied the physics of this, hopefully we can, as we continue to learn more, design a better way. Because it started out as it's a fairly brute force way to do it. You just send a shockwave and you try to hit the stone, and it's pretty good. It works quite well, but there's nothing saying that that's necessarily optimized in any sense.
Sergey?
Yeah. Well, as far as I understand, you experienced with oxalate stones, yes? Will you plan to use, say, phosphate stones or urate?
So Adam can probably speak to this better than I can. I think Adam has tried breaking most all kinds of natural stones. What the cystine stones are the hardest to break? Similar to shockwave?
yes, so cystine, uric acid, struvite, and calcium oxalate, monohydrate, and dihydrate. So that's probably and phosphate stones. So that's probably 95% of all stones, I think, fall in those categories. And we've treated all those types of stones. So
And all broke.
yes.
different level of success. Yeah, I think that it's time to finish maybe. And Wayne and Anne, they are around until Saturday. So if somebody wants to ask more questions, so you're welcome to do so. Let's thank again, Wayne.
Thank you very much.